student, so I'm still a proto-doctor. I have passed my qualifying exams, and now I just have to write my dissertation and graduate. So I'm working with Sebastian and his team. So if you hear me say we and our, that's what I'm talking about. It's the work that I'm doing with my advisor. And we are looking for fast rotators in the Kepler 2 data. So I kind of choose parts of my talk and give you lots of background information about the Kepler mission, tell you what photometry is and how we use that to get something called an autocorrelation function. And I'll tell you what gyrochronology is, which is the thing that I'm most interested in and other indicators of use. And then the second part of my talk will be more about my own research that I'm doing. And so hopefully in the next 19 minutes you guys will know as much as I do about my dissertation. Okay, who's heard of the Kepler mission? Yay, okay, cool. So the Kepler mission was launched, it's a space telescope. It was launched in 2009, and its sole purpose was to look for planets. And the way that it was doing this was that it could point very precisely at one spot in the sky. And so that is, that's what's shown here. And it was able to do this because it has gyroscopes and it has reaction wheels that could keep it pointing and correct so that it could continue to point at this point in the sky. We did that really well for 4 years and discovered something like 3,000 planet candidates. But then I think 2 summers ago, 2 of the 4 reaction wheels failed. And there was the Kepler team tried to fix it, but they couldn't. And so they have reconceived the mission as Kepler 2 or K2. And so now it's using the 2 remaining reaction wheels to continue to kind of point on its side and roll around in its orbit. And it's pointing at the ecliptic. And so the ecliptic is the apparent path that the sun seems to trace out in the sky, and so that is what the Kepler 2 mission is looking at now. And they have called for proposals from different astronomers. We can say this is what we want the Kepler 2 mission to look at, and they choose these proposals and they'll look at the stars that we propose. So my advisor and I are on this list of stars that people are looking at. So what the Kepler, how Kepler works is it's photometry. I guess Rob was mentioning spectroscopy and interferometric data. So the Kepler mission is photometric data, and so it does this using something called a charged coupled device, or it's ECD. It's basically a really fancy camera. So if you ever see pictures from the Kepler mission and they have this weird pattern to it, that's because that's what the camera looks like. And so the ECD collects light that can be stored later for people like me to pore over under their advisory sitting. So what we're doing is we're making light curves. And so this is what Rob has been talking about. This is an example of one of my light curves. The brightness level of these stars are going to change over time because it has star spots. And as the star rotates and these spots appear to come in and out of our field of view, the brightness level is going to change. That's nice. The reason I care about this is because I care to get rotation periods. And so the way that I get rotation periods is using something called an autocorrelation function. And basically what that does is it compares the brightness level with itself at different points in time. And the spacing between the time that we're comparing that brightness level, that's the rotation period. So we're going to test different rotation periods to find the correct one. So this is an example of an autocorrelation function using different test rotation periods and then the actual value of the autocorrelation function. So this right here would be what we call the rotation period for this star. Okay, so the reason that I care about rotation periods is something called gyrochronology. And so gyrochronology is a way to get the age of a star from its rotation period. Younger stars are more active and are rotating faster. They have more spots and they're rotating faster. So as a star gets older, over billions of years, its light curves will change. And so I care about that because I care about the ages of stars, and you've already seen this figure. We did not find this. I care about young stars and the ages of stars in general just because it's going to give us an idea about the ages of the planets that are around it. And if you can somehow work planets into your proposals these days, you'll get something. So, I mean, they are interesting, but that is just it. So I'm going to tell you more about other indicators of use in the second part of my talk, but what we have been doing is looking at the rotation of these stars, and we're looking for fast rotators because those are going to be the younger stars, and then we're going to check for other indicators of these to make sure that we're not wrong. So now I'm going to talk about my own research, the stars that I have been calling super blink KQ. I'll tell you about my fast rotators that I found, and then some more about binary formation because my advisor and I just got 2 NASA grants last week, and so that's probably the direction that my dissertation is going to go, and I've only got 2 slides about it, and that's the direction that we're going. So I'll tell you what I know about that so far. Okay, so the super blink catalog is something that my advisor has been working on since, I think, 2005, maybe before that. What it is a proper motion survey. So proper motion is the apparent motion of stars across the sky against background stars. So stars that are nearby are going to look like they're moving more across the background. So these 2 stars are moving at the same speed, which is indicated by the length of those 2 vectors, but because this star is closer, it's looking like it's moving more. And so my advisor literally is just blinking back and forth an older picture and a newer picture of the same field of the same star field to get the proper motion. And that's shown here. This is a Barnard star, which is the highest proper motion star in the universe, I guess, at least from our point of view. So that's what he's been doing, and in the first year of Kepler 2 data, there are 10,000 super blink stars. And my little Mac computer has computed the rotation period of all of them. And there are 429 fast rotators out of those 10,000. So this is, again, what the Kepler fields look like. This is Hampton 0, 1, 2, and 3. And all these little black points are all stars in the field, and then the different color points are different fast rotators that I found. Like I said, we have 429 so far. And what we have noticed is that their autocorrelation function that I mentioned earlier, there seem to be 2 different flavors of autocorrelation function that we have called stable rotators and decaying rotators, which is a little bit of a misnomer. Like, we just call it decaying because the autocorrelation is itself decays over time and comes back. And so what we think that is actual an indication of the lifetime of the spots on the surface of the star. And if the internet is kind to me, okay, I didn't really think this was going to work. So, oh, yay! Okay, so this is from the NASA SDO telescope, and you can see this is the sun, which doesn't even have that many spots. If you looked at the solar telescope earlier, there was one little guy hanging out. And even the sun not being very active, you can see how much the spots are moving around and are coming in and out. So you can imagine that younger stars, which are more active and have more spots, are going to, the patterns that we see on the surface are going to change over time. And so remember that the autocorrelation function is comparing the brightness level of the star to itself. And so if that spot pattern is changing, the autocorrelation is going to change. And so this is just pictures of the sun over time. That, again, the sun isn't even very active and it changes a lot over the years. Okay, so what we did was we looked at the distribution of rotation periods of these decaying and stable rotators, and we noticed that all of the decaying rotators have the fastest rotation period. So this is the histogram of rotation period on the x-axis and the number of stars with that rotation period on the y. And we originally had those plots where I didn't differentiate between the 2 colors, and then when I separated out the decaying rotators, you notice that they all have the fastest rotation period. So again, we think that that's indicating that the spot patterns are changing, the stars are very active, so it's been very rapidly. So we're just kind of reassuring ourselves that these stars are very young. Okay, so there are other indicators of use, like I mentioned, and one of them is galactic motion. So groups of stars form together in these clouds, like that figure showed earlier, and then they'll move around the galaxy together over time. So eventually they'll be disrupted, but they make clusters of stars with the Pleiades. And so astronomers being astronomers, we like to go out and find these groups of stars, these young groups of stars that are moving together around the galaxy. We call them young kinematic moving groups. And they have characteristic velocities that, if we were to look at them, we can tell if a different star that we don't already know is in one of those groups, if it has a similar velocity, we kind of put them in the same group and say, okay, this star is also young. So we did that. This is a really boring figure, I know, but like this is velocities right and left in the sky, and then up and down in the sky. And so we already know beforehand that young stars are going to have velocities that are kind of clumped around in this area and then pointing down towards the right. And so our fast rotators have this similar sort of velocity. So again, we're just reassuring ourselves that these stars are young. Another indicator is these stars are going to be bright in the UV. Like this is an image of the sun in the UV when it has lots of spots, a little bit brighter. So we're hoping that our stars are going to be brighter in the UV. And unfortunately, they're not really. If they were brighter in the UV, most of them should be over in this area. This is called color polarization. This is like a red color, and this is blue. And our young stars, we were kind of hoping they would all show up in this portion over here, showing that they have an excess of UV light. And we're not sure why. That's something that my advisor is going to make in the future. We just made the plot. Yeah, and this is like similar to what you were talking about. So, yeah, so that's good. When you were talking, I was like, I need to tell Sebastian about this. Okay, so now moving on to binary stars. This is the direction that my research is going to go in. Binary stars have very characteristic light curves. When I look through all of my light curves, I can just say, okay, I know this one is a binary star. And that's because they have eclipses. And the reason that they have eclipses is because the stars are literally passing in front of each other, and it's going to dim the amount of light that we see. So in my 10,000 super blink K2 stars, I have about 25 eclipsing systems. Some of them we already know are binary stars. Some of them are new binary stars. Two of them are planets. A couple of them were new discoveries, which, I mean, new planets are dime a dozen these days. But I care about the actual binary stars. And the reason for that is because we think that these aren't actually young stars rotating rapidly. We think that they might be part of hierarchical triple systems. And so the way that, our justification for that was we thought it was really unusual that all of our binary stars were rapid rotators. And the reason that we think that they might be is because, again, stars form together. And so sometimes you can get these triple systems, and that's not stable gravitationally. So what can happen over time is that two of the stars will pick out the third star. But they'll still remain gravitationally bound to each other, but you'll have two stars that are in a very close alignment, and then a third star where they're all orbiting around each other. And in this process, the two binaries, this double star right here, is going to increase its rotation. It's going to become faster. True physics. So we think that is what is exchanging angular momentum. So we think that that's what's happening. So what my advisor and I just got this funding to do is all of our little fast rotators that we have found that are binary stars, we're going to go hunt around and see if there is a third star that people don't know is there. And this can give a lot of information about because the idea is that fast rotators should be young, and these stars might not necessarily be young. Okay, another commercial break, and this is actually my final slide. Monday was the, I think, second annual Lighthouse Astronomy Night, and Georgia State, we decided to be a part of that. And through logistical reasons, we couldn't actually do it on Monday. It's tomorrow night. I guess relatively near to where we are. It's going to be at Pickeringville Park in North Hall. We have a Facebook event. If you go literally type within CSU/Lighthouse Astronomy Night, you'll find the Facebook event, or you can come after me if you're on Facebook. We're going to have some telescopes set up after sundown, and we're just going to see the stars and talk about astronomy. So hopefully you guys come to that. If you have any questions, I will answer them.
Okay.